Okay, so yesterday we talked about how we could describe limits that were unbounded with an infinity or a negative infinity. Okay, today we are going to talk about limits towards infinity. And in order to do that, we're going to talk about a couple different types of functions that we have dealt with in our pre-calculus days. All right, but our ultimate goal is to look at limits towards infinity. Okay, so I'm just going to remind you, you don't need to write this down, but since we're looking at limits towards infinity, we're going to have a lot of conversations about horizontal asymptotes. And I just want to remind you that horizontal asymptotes is what our function is going to approach either towards infinity or towards negative infinity. Okay? It gives us the ending behavior of our graph. Okay, so we are going to use those throughout some of today's lesson. I just wanted to remind you of their purpose. Okay, I'm going to throw up this same picture here. So what we're going to do is we're going to take limits towards infinity or towards negative infinity. And all that is asking you to think about is what is the ending behavior. If it's positive infinity, what's happening as we go to the end on the right? If it's a negative infinity, what's happening as we go to the end on the left? Okay, so you see for this picture up here, we have a horizontal asymptote. Okay, and that horizontal asymptote is at y equals 3. So when I ask you for the limit towards negative infinity, I know that our graph has to approach that horizontal asymptote of negative 3. And when I ask for the limit towards positive infinity, I know that towards the right, our graph has to approach that horizontal asymptote at 3. Okay? Essentially what I'm doing is asking you for the end behavior of a function. So we're going to talk about some different groupings. Okay? Oh, it's good to see you. Well, have a good weekend, Nathan. Watch the video. Okay. Okay, what I'm going to have you do while I get her situated, I want you to talk about what you can remember about polynomials and what their ending behavior is. Do they fall? Do they rise to the right or to the left? How do you know? What do you remember? All right. Whoever has the longest hair is your spokesperson. Whoever has the longest hair is your spokesperson. All right, part 3. Give me something you remember about polynomials. Aha! If it's an even degree, they're going to end in the same direction. Pod 1. If it's an odd degree, they're going to end in different directions. Okay, so that's awesome. How do we know if they're up or down on either one? Pod 8. Do you have any advice for us on how we know what's happening if they're up or down? Very good. If the coefficient is positive or negative. Okay? So let's go ahead and write this down. So we talked about odd and even. Even is going to have the same behavior. Odd is going to have, opposite behavior. If we have a positive versus negative, LC is just leading coefficient. Okay, the very first coefficient of the highest degree. Okay. If we have a positive coefficient, the right is going to rise. If we have a negative coefficient, the right is going to fall. Okay. That's called the leading coefficient test. You learned it in Algebra 2. You reviewed it in pre-calculus, like probably around this time. That's what we did today in pre-calculus, to be truthful with you. So if I ask you for a limit towards infinity or negative infinity, all you need to do is picture what the ending behavior is. Is it going to fall indefinitely? Is it going to rise indefinitely? Just in and out, in and out.
I know. I'll see it.
Take pretty pictures.
Oh, I wish.
All right, so these are the first 3 functions we are going to deal with. I'll give you a moment to write them down.
Did you say? Yeah, you know how sometimes like when you read, you're like your collarbone goes right down. What did you say? Yeah, it's just like it goes away. You can push it. Yeah. I don't know. Like, I figure out your left side. Oh my god.
That's what I did. I think so. I think he's hanging out already. I'm not talking to him much. I leave him alone. Every once in a while. It's not like that. It's not like that.
Maybe give you one more minute.
Nicole started. Yes, it's actually not. No, we were talking about.
Okay, so here we go. Colby, you're going to help me out. Towards infinity, towards negative infinity. So do we have an odd or even function?
Odd.
We have an odd function, and our leading coefficient is?
2.
Okay,
Positive, sorry.
You told me a fact, it's fine. Okay, so to the right, what's happening?
It's rising.
Okay, so our limit towards infinity is infinity. To the left, what's happening? It's falling. So to the left, to the limit towards negative infinity is negative infinity because we're falling. Okay? All right. Pod 5, who's your spokesperson?
I think it's me.
I think it is you. Okay. 5x squared. Okay? Even or odd function.
Even.
Okay. What's happening to the right?
It's right.
What's happening to the left?
Also rising.
Also rising. We have an even function with a positive leading coefficient. We're rising on both sides. Isn't this fun? Right? Doesn't it feel like we're just doing pre-calculus? All right, so pod 7. Who's my spokesperson?
Bottom is.
Okay, fine. We said negative infinity. And then negative infinity.
Okay. Pod 3. Why would they both be negative infinity? So here you've already talked, right? I've already called on you. So Sean, you get to explain it to me. Because you have the shortest hair. Why are they both negative infinity?
Oh, because the coefficient is negative.
Okay, excellent. At your pod, please complete these two.
I'm so
You just gotta pick out which one to look at. Be careful.
Oh, if they're not ready.
Chloe's got your back.
Yeah, usually the front one.
Okay, next week. What, do you guys work for like dog days?
Yeah.
Okay, so you still have another. Okay. All right, here we go. Raise your hand if you think this first one is positive infinity. Raise your hand if negative infinity. Oh, cool. Okay, pod 1, you keep getting spun. Why is it positive infinity? Okay, leading coefficient's positive.
Please release the ninth grade students to the theater at this
We
time.
don't. All right, raise your hand if you think the second one is positive infinity.
Sit down. Sit.
Positive infinity for the second one. Negative infinity. But guys, our leading coefficient's positive.
That's not our leading coefficient.
Oh, this is our leading coefficient.
I got that right, but
All right, go ahead and write these two things down right here that I'm circling in red. If we have a constant divided by a polynomial, as we go towards infinity or negative infinity, that fraction is going to get smaller and smaller and smaller and approach zero. Right? If our denominator is getting super duper big while our numerator stays the same, that fraction approaches zero. To the r, where r is a power.
Oh, that's an R?
Yeah.
I thought it was like a little apostrophe.
A what?
Alright.
It's a candy game.
R is a positive rational number. Okay, so maybe not necessarily polynomial, but x to a positive power.
What?
The limit as x approaches infinity of 5 minus 2 over x squared. Okay, Eli already has it figured out.
Sorry.
Eli, explain it to us. Do my job.
Oh, geez, now I feel bad.
No, I want you to though. It'll help everyone else.
2 over x squared is 0. So 5 minus 0 is 5.
Okay, here we have the case where we have a constant over x to a power. We're going towards infinity, so that fraction's going to go to 0. So we have 5 minus 0. Thank you, Eli. Give him a hand. For volunteering himself to do that. Okay. Okay, well, what happens if it's not just x to a power? We're not plugging in infinity.
Yeah,
Okay. Okay. No, but you bring up a good point. So, direct substitution is not going to be effective ever with infinity. Infinity is not a number. You can't just plug in infinity. Okay? Anytime you have a limit towards infinity or negative infinity, we do have to think about the graph. Okay? Or there's ways to use this rule right here. Okay? For instance, in this case, okay? If we think about the numerator and denominator separately, like our numerator is a linear equation. Towards infinity, it's rising. Our denominator is a linear equation. Towards infinity, it's rising. Okay, that's not one, people. Infinity isn't a value. Okay? So this is, again, what we call indeterminate. Okay? So if we have this case, yes, we can divide by the highest degree in the denominator. Is it legal to divide the numerator and to divide the denominator by the same thing?
Yeah.
Because then that would be like multiplying by 1. Okay? If we multiply by 5 over 5, that's okay. If we multiply by 1/2 over 1/2, that's okay. That is what we're going to do here. The highest degree in the denominator is x to the first. Okay? So we're going to take the numerator and multiply it by 1 over x. And we're going to take the denominator and multiply it by 1 over x. Okay? Okay? Can we reduce some things there? Can 2x over x be reduced? Can x over x be reduced? Okay. Now we have tweaked this to where we can use the rule that we just talked about on the slide previous. If we have a limit towards infinity of a constant over x, what happens to that? It goes to 0. We have the limit towards infinity of a constant over x. That goes to 0. So what are we left with?
2.
Raise your hand if you knew it was going to be 2. Cool.
Yeah, like take a step back. Like, how did you get to that?
This? So this is basically a trick that I am giving you. If you have a rational expression and the limit is towards infinity, if you take the highest degree in the denominator and divide numerator and denominator by it, we can finagle it to where we can use this rule and determine what the what's left over. Okay, it's just a kind of like how we like multiplied by the conjugate last week. It's basically an algebraic trick we can use to help us determine analytically what we can do or what the limit is.
So you're not dividing by the whole term?
No, we just take the highest degree and we divide everything by that. Okay? We will do another example. However, you don't have to do this much work for this problem. How would I know without doing all this work that it's at 2? What did we talk about at the very beginning? Horizontal asymptotes. Okay? We can determine without doing any algebra that this horizontal asymptote is at 2. Do you remember your horizontal asymptote rules?
Isn't it like coefficient? It's like 2 over.
Since our degrees are the same, we have a coefficient of 2. That is our horizontal asymptote. So write this one down.
Oh. Yeah.
Are the degrees in the numerator and denominator the same?
Yeah.
Yes. Which means our horizontal asymptote is at 3 over 6 or 1/2. And so towards infinity and negative infinity, we are going to approach 1/2.
So we don't have to show work anymore?
Nope. Write this one down. I'm actually going to have you write both of them down.
Yeah.
Notice how in both of these the degrees are different, numerator and denominator. So there's 3 options when we have a rational function. If our degrees are the same, the horizontal asymptote is what the coefficient ratio is. If the denominator has a larger degree, our horizontal asymptote is at 0. Okay, if your denominator has a higher degree, all right, that polynomial is getting bigger in the denominator faster than the numerator, you're going to approach 0. What about when your numerator has a higher degree? What do we have? We have a slant asymptote, or we call them oblique asymptotes. Okay? Which means, I'm not going to make you find it. That's not going to be helpful. But do you remember what those looked like? Right? A slant asymptote, and then they went like this.
Yeah.
Okay, so they're going to either rise or fall. Your answer is going to be infinity or negative infinity. Okay, so on one that has an oblique asymptote, you're going to have to use that trick that I just taught you. So like here, the denominator, its highest degree is 1. So we are going to take each term and divide by x to the first. Almost forgot, sorry. Okay. Well, we know that towards negative infinity, 4 over x is going to go to 0, and 5 over x is going to go to 0. Do you agree? Okay. So what we have is the limit as x approaches negative infinity of 2x over x, which is 2x, divided by 1. Now we have the limit of a polynomial. Okay? Our leading coefficient is positive. We have an odd function. So towards negative infinity, are we going to rise or fall? We're going to fall. So you're seeing that the algebra that we have
Well,
done
why
is
is
going
it
to
not
lead
This
us
is the
to
X.
two X's.
Does that mean it's, they're both gonna like, they're not gonna be going the same way?
It depends if they're in terms.
You know what I'm saying?
And like, if they're only one degree apart, you're only gonna be left with that first.
Yeah.
Yeah, but if they're like two degrees
Oh,
apart,
yeah.
you're gonna have
Does it make sense? It's what it says.
Okay.
I'm like so squirmy right now, it's weird.
We have two examples and they deal with the same function. So we're going to do this limit towards positive infinity and this limit towards negative infinity, and then we get to call it a day and have a 3-day weekend. Okay, so this example and one more.
I have so homework over this.
So.
There's so much.
Write this down. This one is very important.
Write this home and no homework over the 3-day weekend.
That's never. I'm just kidding. Sometimes it is, but not this weekend. Sorry.
We were close.
Okay. Do we have a rational function? Yes. Because it's a fraction. Because it's a fraction. Now, the difference here is we don't have polynomial divided by polynomial, right? If we had polynomial divided by polynomial, we could just think about a horizontal asymptote. Now, this one does have a horizontal asymptote, but it's not as simple as what we did on the previous slide, okay? So, first of all, we are going to use that same method that we just talked about, dividing by the highest degree. But what is our degree in the denominator?
1.
Okay, I heard like this 2 and then it morphed into a 1. Why is it a 1? We have the square root of x squared. So technically our highest degree is 1. So what we're going to do is we are going to divide by x to the first. And x to the first is the same thing as the square root of x squared. All right? So in our square root, we would be dividing by x squared to counteract that. This is too wonderful. You're very good at that. Like throwing things under your breath. Stop talking. Okay. So remember, towards infinity or negative infinity, a constant over x goes to 0. A constant over x squared goes to 0. Were you here when I started this? Okay. It was like that very first row we wrote down. That's the x to the r. That one.
Oh, it doesn't matter what color.
It doesn't matter what power. Okay? So we are left with 3 over radical 2. Essentially, we have a horizontal asymptote that towards the right, we're approaching 3 over radical 2. Okay? Now, I told you that we had another example that looked exactly the same, right? Okay. First of all, questions on this before I go to our last example. Why would I make such a big deal over a similar problem? Write it down. Now we're towards negative infinity.
So that's the next one.
Yeah, that's the answer. So if there's an x, we still need to evaluate it. But once you have a number and there's no x, there's nothing to plug in. We're good. Okay, so we're dealing with the same function, right? But now towards negative infinity. And so our strategy was last time to divide by the highest power in the denominator, which we decided was x to the first, right? So we're going to divide 3x over x, 2 over x. Now here is where it gets interesting. Does x equal the square root of x squared if we are dealing with negative numbers? No. X would equal negative square root of x squared if we are dealing with negative numbers. Questions on that before I go any further? Okay. We can't have negatives under radicals, right? So never would that be a negative x underneath. So what we're going to have to do, if we go under this radical and we take 2x squared and we divide it by x squared, well, that's not legitimate, all right? We're going to have to throw a negative on the outside of this to make that work since we're going towards negative infinity. Okay, we're using negative numbers to do this. Okay, if it was a cubic function, like a cubed root, wouldn't matter because we can have negatives under the cubed root. But since it's even, all right, we got to counterbalance. We got to counteract. So what happens? Our work is going to still look pretty similar, right? But we have that negative on the outside. So towards negative infinity, 2 over x goes to 0. Towards negative infinity, 1 over x squared goes to 0. And we're left with 3 over negative radical 2. This function has 2 horizontal asymptotes. Towards the right, it approaches the positive 1. Towards the left, it approaches the negative 1. Are you interested in what this graph looks like? Okay. You're not going to start your homework in 4 minutes anyway, so it's not like a... Okay, so now I got to find it here. Okay, so help me out. We have 3x minus 2. So 3x minus 2, and then we're dividing by the square root of, is it 2x squared?
Yeah.
Plus 1. Mm-hmm. Okay, so that's why towards infinity we have the limit of 3 over radical 2, but towards negative infinity we have the negative 3 over radical 2. Okay. Okay. Yes. So my advice to you would be at least to show me this step, and then if you know what's going to happen, then that's fine. But I want to at least see that you thought about this, especially with the negative sign. Okay. Okay, let's talk about next week, because like I said, you're not getting us your homework. I get that. Next week, on Tuesday, we're going to do a little bit of work in class, and I'll assign a review. And then your quiz will be concentrated more on the continuity and the limits towards infinity, limits of infinity. Still a few things from the last quiz because it's kind of hard not to talk about those more basic limits. Okay? And then we will review Thursday and Friday. You'll have the weekend. And then Monday and Tuesday of homecoming week will be your test. Okay? So we are done learning new material. I'm gonna give you some resources next week to help you keep all the rules straight. Cause individually, it's not bad, but when we put all of the rules together, we gotta remember which goes with what. So this weekend, I really need you to, do your homework, okay? And if you are missing any homework, I really need you to get it done over the weekend, that way you're up to speed Tuesday, okay? Yeah, remember my videos are online, so if you need to reference anything Monday night when you're like, oh my gosh, I don't remember what we talked about. Okay, my videos are online, which I'm gonna stop now.